All right, all y'all, this is the final chapter, and we're going to kind of one step at a time kind of build up our momentum, like climbing up to the top of a roller coaster, and then it's all downhill, and we're going to move pretty fast. So this will probably be 2 parts, but here's the first to kind of build up to it. So here's what we're going to try to go over with parallelism and parallel processing, so to speak. It's not exactly what you guys might traditionally think of as parallel processing, but we'll talk about it. So these are the things we're going to try to cover. To do that, though, we're going to go backwards here a little bit. So here's where we're going to build up some momentum a little bit at a time. So going back to chapter 2, if you remember when we first introduced parallelism in data as finding something that could be repeated or a common pattern that could be turned into parallelism, we just simply talked about instructions. So in chapter 2, let's see here, we just went over and I talked about a data race because at the time, here we go. We didn't want to get into a lot of information, so we just talked about, we focused a lot on a data race, and we talked about how in the book what you can do is use special commands to lock a certain word that's loaded so that it can't be modified with by another processor or core without synchronization, because it requires synchronization. So chapter 2, we kind of first introduced the idea of synchronization. Then in chapter 3, we went a little bit further. We went into, let me pull it up here, subword parallelism, and we'll talk about Appendix B here also, but basically right there again, finding the pattern, and so that if the same operation is being done, if that's the instruction set, then, and it's being done on different data, so this is different than the example we gave in chapter 2, then we have a situation, the conditions are right so that we can do multiple instructions on different pieces of data. So we can call it data level parallelism, or we introduce the term here. We're going to talk about it more explicitly in Flynn's taxonomy, the single instruction multiple data, SIMD. And so we talked through that, and I didn't get to mention it a lot, but we talked through, in chapter 3 it also mentions there's advanced what's called vector extensions, where we can treat a set of registers as all in order, not executing them one at a time, but executing multiple instructions in parallel, and each register has different pieces of data. And some processors offered this through AVX, and you were asked multiple choice questions on it, but chapter 3 goes more in detail on it. We're going to talk more explicitly about vector operations here in a second. Let me see if I can get to, there's a good section in the book. It's here, and then chapter 4. So let's talk about chapter 4. So let me get back to, so then finally chapter 4, where we talk about parallelism, advanced instruction level parallelism, so where we get more into instruction level parallelism, and that's where I was going with this. So the book has a pretty good section here in chapter 4 in 2 parts on parallelism via instructions, and it talks about right here static multiple issue, dynamic multiple issue processor. But again, kind of building up our momentum here, kind of refresher. In chapter 4 we discussed how you can loop on roll. So if you have a loop such as this one, you cannot, let's see here, let me find where it starts, such as this one right here, right? We can unroll it, and you can find different parts to it, like data transfer parts and ALU parts, and accomplish them if you have a multiple issue processor simultaneously. And so there's a couple ways to deal with this, right? And let me see if the book talks about it here. Yeah, it does. So the two ways you can deal with this is right here. In instruction level parallelism, going into detail, and right here the book does a good job talking about it, is we can change our pipeline, right? So instead of 5 stages, we can have 7 stages. And remember, we went over the calculations for an increased pipeline. Theoretically, you can increase your parallelism by factors of improvement. And so one option is to increase the stages in your pipeline. The other issue, right, using the book example of a washer, a dryer, someone sorting, and then someone folding and putting away, is you can just have multiple instances of that same pipeline, right? And this is what multiple issue is. So it talks about right there with we'd replace our household washer dryer with, say, 3 washers and 3 dryers, and more instances to fold and put away in the same amount of time. So what that might look like is, right, they do a pretty good picture right here, right, as we take, this isn't the fully developed MIPS CPU data path, but it's simplistic. So we take our standard data path right here, right, and we duplicate it. So this is assuming not only we're not just dealing with 1 bit anymore, maybe this is an 8-bit or 16-bit or 32-bit or 64-bit word through here, but also you can send another word through here and see how they access the same registers here. So now you create what's called multiple issue, where we issue multiple instructions, right, on data at the same time. So we take a traditional loop like this, and this just breaks it into parts, so we can issue these instructions in parallel. But what's more valuable is we can completely unroll the loop, and then we can accomplish these tasks simultaneously, issuing 2 instructions at a time. The step diagram looks like this. There's a pretty good step diagram, if I can find it now. Yeah, here's the step diagram, right? So this is, again, highly simplistic, but just to kind of get an idea seated in your mind here, right here, right, issued at the same time, and both going through different data paths but on the same CPU, they go through fetch and decode simultaneously, and then they use different data paths. So one of them goes through ALU data path, the other load store data path. So the first might use the traditional ALU that you can see it might need for actual arithmetic operations. The other just uses the ALU relative to a data memory type instruction, and then accomplishes right back when it's all finished. So that's what would be considered multiple issue, and this example right here is kind of the stair-step model, is traditionally a static model because it's issuing them in parallel, and it's already decided ahead of time which instructions can be issued in parallel, and that's about as far as I'm going to go into it here. That's static. Now multiple issue dynamic is a little different because it's also called out of order execution, or an out of order, I'm trying to find it right, yeah, out of order execution, but a dynamic scheduler is required, and what it's a little more, it can be more complex. Again, the book here, what's out in industry, is far more advanced than this, to my conclusion, my guess here. But here are some simplistic examples, is that you break it up into tasks, right? So you might have one instruction fetch and decode unit, and then depending on once the instruction is decoded, it might go down a data path. Again, these could be simultaneous for whatever it's doing, and like integer operations, floating point operation, load, store. I mean, we've talked about in the class how modern processors, right, will have a whole dedicated area for floating point operations explicitly. because of the amount of work that it takes, right? So there's definitely some dynamic scheduling going on. Now, dynamic scheduling obviously adds significant additional management to check data dependencies amongst the other dependencies and ensure that the out of order execution will not negatively impact the results of the operation. Okay, so this was pages, you can look further into this, and it starts at 334, I think, in the book. 332, where are we? Here we go. 410, which is 332 in my book, and it goes for about 10-15 pages. Okay, so again, we're just building. So that was chapter 2, chapter 3, chapter 4. Now in appendix B, remember, we saw additional methods that we can increase all the way down at the ALU level, right? When down at the bit level, where we had a carry on an adder, right? And instead of waiting for the results through each of those adders, right, or ALU, we created an equation to represent the, right here, here's the equation, the carry operation and what's going to be carried in binary, and then we can accomplish them in process like this. So here was some additional parallelism that we talked about. And then finally, let's see here, and most recently in chapter 5, we talked through cache coherence. We didn't talk a lot about it in the post because I had your peer go through it with you in class as an example, because really a hands-on example I think is the best way, as with many of these things, to understand it. Oops. But I can talk about it briefly here in chapter 5, right? That ultimately, when we have these processors that have multiple cores or multiple processors in a single device, what's going to happen is now we have shared memory, and so we need coherence. We need some sort of way for the reads to return the most recently written value. And so you guys did some examples in class, ensuring, see, here's an example of 2 CPUs and shared memory. And here's the state machine that I think I mentioned this in the chapter 5 video, but that goes through the state of dealing with coherence in a cache. Okay, so that was kind of the roller coaster ride up. So now we're at a place where we can kind of get like it's a really high roller coaster, like a 10,000 foot view, all right? So we can kind of see everything big picture. I'm going to introduce a few more concepts in this chapter. We're going to talk more in detail about vector operations, and we're going to talk about threads and processes. So let's talk about threads and processes now, because I guess we'll ink up on the chain here a couple more steps before we go down the hill on the roller coaster. So let's get into what a process and thread are, and let's talk about that real quick, because the book just kind of briefly mentions them. Multi-threading is the norm today, and so when you get into application and industry, you're going to need to know how to deal with, decode, work with, debug multi-threaded programs. In fact, recently at one of my kind of gigs that I was working, that was the very issue we had, is we had someone who did multi-threading on a unique one-of-a-kind system. They built unique one-of-a-kind code for it, no instruction manual, etc. Anyways, all sorts of hindrances, which you guys will learn more about in your degree program. But long story short, there was a data race that was being created by multiple threads, and so they were getting different results every time. And so that was something I had to fix. So thanks God, I got that, with his help, got that fixed. So let's talk about what a thread is, because the book just right here kind of, oh, by the way, puts this out. And I'm not knocking on the book. I mean, it's a lot of material and they do a good job, and we can't talk explicitly into what they are, but it gives a good definition right here, right? A process includes one or more threads, the address space, the operating system state. So processes, right, are invoked and handled by the operating system. Okay. Whereas a thread, so what's the difference between a process and a thread, right? A thread includes the program counter, the register state, and the stack. It is a lightweight process, whereas threads commonly share a single address space, processes don't. So pthread is an industry standard that's out there, and basically what it does is when you create a thread, it makes like a mini instance of the process that generated it. This is just a simplistic example. So it has all the ID and information of the process that generated it, but it has its own, like it says here, lightweight version of other information. It can now be separately fed through the CPU or cores, depending on how you invoked that thread from its original parent process. Okay, so that's process and thread. All right, so let's start putting this all together. So now here we go. We're going to start heading down that roller coaster. All right. So parallel programming is fun. It's challenging. I think it's fun because you're no longer just considering process. The whole course we've talked about a standard measurement, right, and benchmarks and throughput, and so that's still the goals here. The same goals apply here, but now you need to find a way to do it that's relevant, that makes sense, right? For example, if you have operations you're doing on some matrix, right? If you just do them in any order you please, right? And theoretically, it'd be possible to divide up matrix operations to, 100 cores, perform the operation, give the result to the user and say, there you go, we did all the operations. But obviously the order begs relevance, right? So if there's not a proper order to those operations that you accomplish, then the final data has no relevance, right? We talked early in the class about this as order of operations and standard mathematics, right? So parallel programming introduces all sorts of challenges, right? Because we want to get, and often it's a significant, so some factor performance, like 2 times or more. That's a whole other conversation. But we have to now deal with synchronizing the data, right, which introduces communications overheads, and how we partition out each of these operations that are being done, right? Maybe it can be broken up into tasks. Maybe it can't. Okay. For example, all right, to give an example mathematically of how challenging this can be, in the book is kind of better demonstration than the slides here. If we want, right, an improvement of 90 times, okay, that's a significant, very significant factor of improvement. But we say it's so important, right, we're going to parse out this original operation algorithm to 100 processors, okay? So remember Amdahl's law here, we talk about, remember, the speed up is only as fast as the, can only be attained to be as fast as your longest sequential part. So if we talked about this way early in this semester, so if you have a task that's being accomplished in parallel, if there's one part that has to be done in sequence and all the other parts have to wait for it, that will be your greatest improvement. It's only speeding it up to the extent of that one part that has to be done in order last, right? So we gave this formula, so we can kind of reverse engineer if we just change it from execution time, right? And we do some divisions, we create speed up, right? So you can see right here, we added in here the execution time before, right, doing the division and then spreading it out. I'm not going to go into that step by step here, right, to get the factor of speed up, right? We can see here if we do the math, right, and we say, okay, we want a 90 times, so factor of 90 speed up, right, for 100 processors, right? that basically right here, simplifying and solving, to achieve this, only 0.1% of this algorithm, whatever it is, can be sequential. The rest has to be parallelizable, has to be dividable. This is pretty unrealistic. Most sequences that I've dealt with have much larger than 0.1% part that's sequential. So this is a challenge. This is an interesting challenge because often people have the mindset of, oh, we'll do parallel processing and that'll solve all the problems. That's just not the case. So there's something called strong versus weak scaling. Strong scaling is where a problem size is very attuned to scaling. It's very easy to parallelize it. And the book goes over the math for this. Weak scaling is where the problem size grows proportionally to the number of processors. So it begs the question of, is it worth parallelizing? So those are just some big picture terms, okay? Now, here's finally Flynn's taxonomy. All right, so Flynn's taxonomy, we've talked a lot about this in class. I mean, 99% of our time has been on single instruction, single data. And we've talked about it at the instruction level, and that's why I mentioned earlier instruction level parallelism, right? Where basically we pipeline through one instruction at a time on one piece of data at a time, okay? On the other end of it, what we consider traditionally parallel processing is multiple instruction, multiple data, okay? This is also known as single program multiple data, okay? Because usually there's some relevant context that a program process, like I introduced the term earlier, is executing in to keep all the data valuable and the final result and the order, okay? Now, because of this taxonomy that was introduced in the 1960s, now you have, which let me talk about this, right? You have instruction streams, right? So how many streams of instructions do you have? And data streams, okay? So single instruction stream, single data stream, okay? Multiple instruction stream, multiple data stream. Because of this, you get on the horizon here on the pendulum, you get these other two. You get single instruction, multiple data, and multiple instruction, single data, okay? So you get these two different portions also as a result. We're going to focus talking mostly about this, about single instruction, single data, and multiple instruction, multiple data. And it gives some examples here, okay? All right, let's talk through, I'm going to come back to this area because we've already talked through some of that. Let's talk about threading, okay? So up until this point, right, we've always had this assumption that we're operating, and as you've applied in class, you built one program, right, and executed it as one process, okay? We didn't thread it out, and that's kind of outside of the context of this course on how that all comes together. But let's, for now, treat a single process as just a single thread, okay? A single process can have multiple threads, but let's treat it as one thread. Well, you can create this nice little visual on what multi-threading, right, looks like on a processor, okay? So let me see if there's anything I want to talk about there afterwards. So here's the definitions we went over earlier, right? A thread, it's like a mini version of a process, okay? And we can create a hardware utilization of threads and processes to parallel process, which is called hardware multi-threading. So the operating system, right, has to make a decision at some point to switch between processes and or threads. How it makes that decision and what it does is a whole other course. But from a perspective of performance, we can talk about it here a little bit, right? And the book, and this is the common accepted term in industry, it talks about either fine-grained or coarse-grained or kind of a hybrid of it. SMT, I'll pull the text up for that in a second. But one idea here, fine-grained multi-threading, is that every instruction, we switch to a different thread. All right, so maybe you're running a computational program that's just doing math. Okay, so it's issuing add, sub, divide, whatever. And maybe you have another program that is you're surfing the internet, right? So you're mostly pulling data into cache, okay, and then it still is going to do some operations because of display, which we'll talk about that in a little bit. But between those two programs, right, and their relevant threads, in fine-grained, the idea is simplified hardware ideas outside of the operating system. At the hardware level, we just switch between these threads every instruction, okay? Whereas a coarse-grained solution is only after significant events such as last level cache miss, so whenever a significant stall might be occurring in one, then we switch to the other. Or maybe a trap is executed, which means the operating system is invoked. And when the operating system is invoked and control is taken away from the process that's executing and given to the operating system, then maybe a coarse-grained thread switches, so a whole other process starts running, such as the operating system or another process. Here's the visual I wanted to get to because these are actually kind of useful. The idea here is, like we talked about earlier with multiple issue, is right here on the horizontal you have how many instructions can be issued. The little black, blue, and multi-gray colored here are different instructions, and it's presumed they're fully completed through each pipeline. That this is like a pipeline here, here, here. So as time progresses, okay. So in just operating one thread at a time, right? Thread A, for example, in this multiple issue, maybe it's the order of data or sequence of events because of control branches, but for any reason, only 2 instructions can be issued and processed and completed before this instruction is issued and processed completed, and then these 3 instructions, and so on. Okay, so maybe the dynamic or out of order scheduler issued them in this method, and this is the only way it could be done. Whereas thread B, first 3 can be issued, then 2, and then 1. So maybe these are all data dependent on each other. Okay, and then thread C looks like this, 3, and then you can see there's a huge stall here. So maybe it's waiting for a user input, some other event. And thread D, similar, has a slight stall. Thread B, you can see there's a slight stall here, and thread A has a huge stall here. So if we just executed thread A, right, without hardware parallelism kicking in, so no fine, coarse, or SMT multi-threading going on, then basically you can see the time right here that it takes to accomplish this, okay? Right here. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9 units of time. In the meantime, right, these parallel data paths in the CPU or cores, no ops, or something must be getting issued in all this wasted time. Okay, same here, here, and here. So this is process dependent, or thread dependent in this case, that the instructions get issued in this order. So again, this is one instruction, another instruction, these 2 lanes in the data path are wasted. Now 3 are wasted, and so forth, okay? And then this is time as we go this direction, right? So at a hardware level, we can offer some solution to this. The first easiest thing to discuss is coarse-grained multithreading, right? Coarse-grained multithreading is just going to say whenever there's a major event, right, such as right here, maybe the operating system was invoked right here. See, there's 1, 2, 3, looks like full pipeline stalls before it can continue. So in coarse, at that point, you can see there's a stall here, and so we recognize it, and so now we take control away from the processor to this thread and give it to thread B. So now, while we're waiting for whatever reason, maybe it's user input or a trap or whatever is going on in the operating system here, thread B begins to execute. So we only waste this time here, okay? So that's coarse-grained. So like I said, a major, some significant event, okay? Or maybe it's a cache miss. We're waiting for, that's a good example, data to be written from hard disk to RAM down to cache. So it's a really worst case miss. Okay, that would make sense why there's a large gap here. Okay, fine-grained multi-threading is more refined, obviously, no pun intended here, right? And so every pipeline or instruction cycle here, you can see it switches between threads. So thread A issues however many instructions it can. Thread B then issues however many it can. Thread C, then D, and we just kind of, this is like a round robin scheduling here of each thread. Okay, so each one is just given one unit of time on the processor. Okay, and then finally we kind of get this hybrid, which the book does a pretty good job talking about. So we're going to pull that up. Right, called simultaneous multithreading. Right, and so similar to other hardware dependencies, right? Now we depend on the hardware, as it talks about right here, to exploit instruction level parallelism, right? And multiple issue processors, right? And it determines, right? Let me just read it. Since that's utilized existing data, yeah, it does not reduce every resource every cycle. Instead, SMT is always executing instruction for multiple threads, leaving it up to the hardware to associate instruction slots and renamed registers with their proper threads. So, as you could guess, we're adding additional management requirement here, but we're implementing it at the hardware level. So if done well, it's really not a loss. It will be an additional cost in design and development and in building, but the payoff, right, is in performance, as you can see. And this is like a very best case scenario, but it finds something to execute in every cycle, in every data path. So for example, in instance of time 0 here, it's executing 2 instructions from thread A and renaming and keeping relevant tabs on their registers, and it's executing 2 instructions from thread B. Next cycle, right, it finishes the initial portion of thread B in order, and then executes all of thread C in order. And then third, or 0, 1, 2, second time instance, right, it's accomplishing thread D, and then it's going back to A, so somewhat of round robin again. But that is what it calls simultaneous multi-threading. Okay, so it's kind of a hybrid of both, and I mean fully optimizing the time and use on the processor. Okay, you might want to take a break here and go back. Like I said, we kind of built up and then we just start cruising downhill. So this level of understanding depends on you understanding processes and threads. For now, where you all are at in your degree program, if you just think of a thread as a different process, that's sufficient. But understand that process is going to have multiple threads. Okay. All right. Let's talk about vector versus scalar. Vector was introduced briefly in the book earlier, and it's kind of touched with the AVX instruction set. Let's talk in detail now about how this can be taken advantage of. Okay, and the book again does a pretty good example talking through this. So we'll go into the book here. So it gives an example, and it gives credit here, then it is worth mentioning, right, to Seymour Cray. He's kind of considered the father of parallel processing today, and relative to this class, he had a lab here in Colorado, and that's a whole nother discussion, but some really cool stuff. So vector processing comes about, the idea of what Cray talks about here is that it's really cool to have a parallel system, but a parallel system is only as good as how well you use it, right? So it talks through here. The idea in vector parallelism is to collect data elements from memory, put them in order into a large set of registers, and operate them on them sequentially in registers using pipelined execution units. Okay, what does that look like? It looks like this. So the idea is that traditionally, here's what we've kind of been focusing on, right? is a single stream, right? And let's say this is the addition of A and B, okay, and it gives us the result C. Now the idea is if you have a matrix, for example, where you are accomplishing this operation, right, and you've already accomplished A times X for every element in this matrix, okay, so now all you need to do is add the result of A times X plus Y, then there's some very reasonable parallelism here. You can just, if you have multiple data paths here to operate and accomplish this, right, then you can essentially just issue multiple instructions to each of these data paths to add these individual array elements because there's no data dependency. So this is a vector operation, all right? And the book, I like what it goes into, for example, is it gives the example in MIPS of we can now take our initial instruction set architecture and change it to include what's called vector operations. So basically in this kind of benchmark test here, the DAXPY, right, double precision A times X plus Y, right, we can now do scalar. So let's give an application. Here would be the traditional MIPS code for accomplishing this on a matrix, right? So you have to have a loop, right? So you load A. A is a scalar value, so it's the same for all, okay? And then you find out, right, the upper bound of what to load. And then we do a loop right here. We load X, we accomplish A times X, we load Y, so then we add the result of AX and Y, we store them, we do loop overhead maintenance here, right? We check a bound, we see if we're done, and then if we're not, right, we go back to the top, okay? And we just repeat this. Now, we've already talked through in the class how we can unroll this, so we could easily unroll this, right? But what if at the instruction set architecture now we can create hardware to implement the unrolling, and that's exactly what vector operations do, right? So we load the scalar, again it's just a single scalar. Now we load the vector of X, so we load all of X. So that means you must have as many registers available in this pipeline as you do values in X, or less values in X than you do registers, okay? And then we accomplish the multiplication, right, between what you loaded, right, and the scalar, right? And then we load Y into all of these, add it, and then store it. And the idea is that all of this is done in data paths simultaneously. So this picture we already showed in the slideshow, but as it calls it, kind of vector lanes here. The gain here is immense, both in application and in computation, because now the pipeline will definitely be filled. All the data paths theoretically can be filled, and accomplishing this as the programmer, thanks to the vector instructions that they've added, makes it very simple, okay? And we'll talk about this kind of the solution in GPUs. Okay, I think this is a good breaking point for the first video. Next video we're going to go into more detail here with other parallel processing and what it means and how to do it.